for our webinar on power measurement and analysis of switch mode power supplies. My name is Hillary Lustig, and I'm the Marketing Communications Manager for Teledyne LeCroy. For some of you, this may be your first event with us, so I'd like to take a minute and introduce our company to you. Founded in 1964 by Walter LeCroy, we are a US-based company headquartered in Chestnut Ridge, New York, where many of our oscilloscopes are designed and manufactured. We were acquired by Teledyne Technologies in August of 2012, and our name changed to Teledyne LeCroy. Our current real-time oscilloscopes range from 40 megahertz to 100 gigahertz real-time. Our presenter today is Stephen Muller. Stephen received his BS in mathematical physics from the State University of New York at Buffalo. His career has been focused in test and measurement industry, working previously for Agilent, and now as the Applications Engineering Manager for Teledyne LeCroy, where he specializes in signal integrity and high-speed serial data analysis testing solutions. Before we begin today's presentation, just a few housekeeping items. In an effort to keep us running on time, we will be answering all questions at the end of the presentation, but we do encourage you to send in your questions at any time during the presentation using the questions section on your control panel. In addition, this presentation is being recorded and will be available to view on demand later today, and a link to the recording will be sent out in our follow-up email. Thank you again for joining us. We know how valuable your time is. Steve, I will now turn the presentation over to you.
Okay, thank you for the introduction, Hillary. So today we're talking about power, which is a pretty broad topic, and we have some other webinars that focus on other areas of power measurement. So we have a series of webinars now that are focused more on three-phase power and motor drive analysis. And I've done a webinar in the past that had some focus on power integrity, but this is going to be looking more at switch mode power supplies and mostly around this power analyzer package that we have to do some measurements on these kind of power supplies. So we're going to try to cover a good amount of stuff today, starting with the AC input to the power supply here and looking at some of the measurements we can make, including some power measurements, efficiency, harmonics, and compliance measurements. And then a lot of the presentations are actually going to be on the switching transistor itself, which might be, a MOSFET or an IGBT, and the losses and measurement challenges and some other things around the transistor itself. Also talk a little bit about transformers, control loop behavior and how we can analyze different kind of dynamic conditions there. And then finally the ripple on the output of the supply if this is a AC to DC power supply. Okay, so the first piece that we want to look at here is the input. So I have a simplified diagram here showing what a switching power supply might look like. And the AC input here, we have a section that's basically going to rectify the input signal here. And then you have so that's represented by the diode at the top. And then we have a large capacitor that's going to store the energy here and really act as a DC bus beyond that point, which is going to feed the switch. So the capacitor here is going to maintain essentially a DC voltage across it, and it's really only going to draw power from or current from the AC input when the AC voltage exceeds the voltage on the capacitor. And since it's a large capacitor, we end up discharging it pretty slowly, and so what ends up happening is when we look at the current of this, we should see really that just when the voltage waveform gets to the peak, we should see a pulse of current that gets drawn from the source here. So it's really not a steady current draw, it's really more of a pulse current draw. So if we look at the next slide here, this is going to show us making this measurement here, looking at the line voltage, line current, and then we can calculate the power from that by multiplying those two waveforms together. And this is just what we expected to see based on what I described before. So we see a nice AC sine wave as the input voltage. And you can see we're making a measurement down here at 50 hertz is the frequency of this input. And then only when the voltage gets to a voltage that's higher than what's on the capacitor will this actually draw any current. And so you can see you get this big spike of current at the max and at the min here. And we have some measurements that were displayed at the bottom here. So this is done again using our automated power analysis package. So this is going to calculate for us the RMS voltage, RMS current, and then we have the real power, apparent power, power factor, and the crest factor. So the interesting thing here is the real power and apparent power are different by almost a factor of 2, and that's what's the ratio of these is what gives us the power factor, and that's why we have this power factor around 0.5. And this is really driven by the fact that we have just this pulsed current. So ultimately what we get is we get a lot of the power reflected back and not actually used by the device. So the difference between the real power and the apparent power is the real power can actually be used to do work by the system. The apparent power is just the voltage times the current, and the difference of that is what actually gets just reflected back to the source. So this is really not ideal to have a power factor that's this low. This can cause a number of problems. Basically, you have to design the input of the power supply to handle a current load, which actually can't be used by the power supply itself. So you have to over-design the input to the supply. And actually, it's also going to contribute to heating of the wire in the building that you're connected to, and increase the stress and the heating on the utility transformers, and everything going all the way back to the utility electric supply. So this causes not just problems for your particular device, but everything upstream. So because of this, and also another factor, there was a standard created called this EN 61000 here, and what this does is it specifies the harmonic content of the current draw from the power supply. So this, by coming up with this spec here, it basically ensures that all the devices out there that are drawing current, they're not going to be injecting harmonic content back out onto the mains power. And the harmonics alone could interfere with other pieces of equipment that are connected, but also that harmonic content leads to a poor power factor, which again is going to increase the stress on the whole grid. So this is the standard that was created to come up with some limits for different classes of equipment, and it measures it sets limits for the current and the voltage at different harmonics here. So this is one of the tools we have in our power analyzer package here is the harmonics analysis. So this will automatically look at the voltage and current signals we have. It'll calculate the voltage and the current for each of the harmonics, and it'll compare it against the spec. So here you can see, if you follow these arrows, this is an excerpt from the spec up here, and you can see we have the limits already programmed into the software here. So you can see these match up with the arrows. And then here's the actual measured values, and we'll compare those to the limits and show you pass or fail. So again, this is an important test for a number of reasons. One is that it's going to make sure you have a high power factor, and that you can actually reduce the amount of harmonics current that you're sending back out onto the mains power. So here's an example which is different than the first one we looked at. Again, we have our voltage signal on top. The current is in the pink trace here, and then power being green. So this is a device that has some power factor correction circuitry implemented in it. And this gives us, you can see the real power and apparent power are very similar. And then, of course, our power factor is going to be very close to 1. So a lot of devices have some power factor correction built in, which adds some cost and complexity to the design, but overall is going to make sure you have a good power factor here. Another measurement you might want to make, which would involve the input and the output power, would be efficiency. So in this example, we have in channel 1 here, and the yellow trace is the voltage. We have current on channel 2, and this is the input and input voltage and input current. And then this is an AC to DC power supply, so the output is a DC voltage and current that we've measured here in these two waveforms. And then, of course, we can calculate the power. So here's the input power and the output power. And if we divide those, then we can get the efficiency here. So we can see the calculated input power at around 95 watts and the output power around 80 watts, and that gives us an efficiency of somewhere around 84%. So obviously, there's going to be some losses through the system. And here we can quantify what those losses are. But the other tools that we have in this package really allow you to dig in a little bit deeper to understand where those are coming from. So, for example, we have switching losses, and we have some other measurements, which I'll talk about in a second, that would actually go in and look at those switching losses. You might also have some losses in the transformer, so we have some tools to look at that as well. So this is a good overall number to show you the efficiency. If you want to understand where that's coming from, you have to dig a little bit deeper with some of the other tools here. So the next piece I want to talk about here is actually the transistor. But what's interesting about these kind of power supplies is regardless of whether you're going from AC input to DC output, or you're going DC input to AC output, or any combination, typically you have some kind of an inverter section inside of the power supply. So really here our AC input gets converted to DC, and then the DC gets chopped up by this MOSFET here, which will send that AC signal then through the transformer, and the output here is really AC, and then that gets again rectified into a DC output. So while a lot of this presentation is focused around AC to DC power supplies, really all these switching type measurements are applicable to any configuration that has some kind of an inverter, is using some kind of a switch here to convert the power somehow. So here's a couple examples of other applications besides just the standard AC to AC to DC converter. So for example, over here on the bottom left is slightly more complicated design. This is a motor drive here. So you have a 3-phase input. Again, that's going to get rectified into a DC bus. And then here we have this cascaded H-bridge topology, but it's really just 6 switches here, 6 transistors that are going to create some kind of AC output here. So if you want to test and characterize the efficiency of that motor drive, well, you need to look at what the switching losses are for these. And so even for configurations like this, the switching loss measurements and a lot of the stuff we're going to talk about is applicable. Same thing for here's a PV inverter, solar PV inverter, where we have a DC input that's coming from the PV array itself, and then a number of different switches, transistors, and transformers and things, and finally an AC output that's going to be fed back to the grid. So there's a lot of places in power electronics where we have transistors that are used to switch power, and anytime you have that, the type of measurements we're going to talk about here are very useful to look at. So here's an example of, this would be a source to drain measurement on a MOSFET, and we're looking at the top signal here at the voltage. The middle is the current, and then we have the power on the bottom. And what you'll see here is it's split into different sections here. So we're starting off here, and the voltage is very low, and so that means the switch is closed and we're conducting current through it. And if you look down at the current trace, sure enough, we have some positive current flowing through the switch. Then we have the switch opening, and the voltage goes high in that case, and we go down to 0 volts here. And then again, the switch is going to close, and we're going to conduct some current. And this is how we control the amount of power that actually gets delivered to the load, is by how much of the time we have the switch closed versus have it open. So you'll notice that the power analyzer package will automatically identify these different zones or these different states. So you can see it's labeled this conduction. Here's the turn off, off state, turn on, and conduction again. And it's really nice to have that because it's going to automatically calculate the losses here for each individual state. So you can see we have the turn off, conduction, turn on, conduction, turn off, off state, and the total losses here, plus the switching frequency. So all of this stuff is calculated automatically as soon as you turn on the measurement here. In this case, we're displaying the loss here in joules, which is essentially going to be the integral or the area under that part of the curve. We can also display it as a function of time here, so power is going to be the energy per unit time. And so we have the same signal here, but now we're displaying the losses in watts instead of joules. So once you have the measurements set up, it's fairly easy to actually make the measurements with the software because it's done automatically. But there are a number of challenges with actually configuring everything to make these measurements and getting everything set up ahead of time. One of the big challenges here is that you have a really high dynamic range measurement you're trying to make. And what that means is we have a signal here that in this case is about 250 volts peak to peak. And we have a section here which is the conduction state here. So when the transistor is closed and we're conducting current, the voltage is very close to zero. And if you want to be able to characterize this conduction state well, you need to measure a voltage that's maybe a 1 volt, and at the same time you're measuring a voltage here that's 250 volts, which is the peak to peak. So this is a really difficult thing to do, and you'll see the issue and this zoom in here is if we actually just zoom in on the saturation voltage here, you can see what that looks like. So the reason we're interested in measuring this very precisely is because while we're conducting current there, we want to have a very low voltage, a very low resistance, so that we're not getting a lot of heat loss there. So we want to be able to measure that very closely. But you can see if we zoom in on this state here, what happens. So this is the resolution issue that you have and the dynamic range issue you have on oscilloscopes, which have these 8-bit digitizers, so that if you capture the whole signal and you zoom in on one piece of it here, what you'll see is these are the quantization levels of the ADC. So these different levels that you see here, these are the different codes for the ADC where actually a voltage sample can be stuck into. So this is a difficult measurement to make, and it's one that LeCroy is very good at making, and we have a few solutions which I'll present to you today. There's other scope vendors out there that'll tell you that you should just look up the resistance value from the data sheet and you should plug that in, and then from there you can convert to voltage with the measured current. But I think that the point of having the scope is to be able to measure this stuff yourself, and if you're just going to look at a data sheet, that kind of defeats the point. So we want to actually make the measurement, not just trust what it says in the data sheet. So we need a way to actually make an accurate measurement on this, and I'm going to show you a couple ways that we have to do that. So the first thing you might ask is, well, why can't we just adjust the vertical scaling on the scope so that we zoom way in on the signal, the piece of the signal we're interested in, and then that way we can use our resolution, our 8 bits of the ADC just on the piece that we're interested in. And you can do that, but the issue with a typical differential probe or the input amplifiers on the scope is you get a signal that we see in green here. So as soon as you overdrive the amplifier in the probe or the scope, it's going to go nonlinear, and you have the amplifier gets saturated, and then even when you come back into the range of the amplifier, there's some time that it takes in order to recover and have a linear response and give you an accurate measurement on the scope. So you can see what happens here. We overdrove the signal off of the screen, and now it takes a while to settle back down here. Now LeCroy sells a differential amplifier, which is not a probe, it's an external unit that's a differential amplifier. And it has a couple of key advantages, and you'll see one of them here is the extremely fast overdrive recovery. So right away, this amplifier is going to come right back into a linear state and start behaving normally and giving us good results here. So this is the DA1855A differential amplifier, and this has been the, I would say, the standard way to make this measurement for a long time. You know, we have a huge number of these amplifiers out there in different power labs, and this has sort of been the golden reference for these kind of measurements. And there's really two features that differentiate this from other products out there. One, again, is the overdrive recovery. So you get 400 volts to 100 millivolts in less than 100 nanoseconds. So you can really blast the amplifier with a huge amount of voltage, and then it's going to recover right away as soon as the signal comes back onto the screen. The other one is this common mode rejection ratio of 100,000 to 1. So this is a very good CMRR spec, and this is important because when you're making power measurements, you're typically probing in a very noisy environment. And one thing you'll notice, if you try to use a single-ended probe for a lot of these measurements, it can be disastrous because you have so much noise that gets coupled onto the probe and shows up directly on your measurement. And if you use, for example, a long ground lead, that'll make things even worse. If you're using a single-ended probe, you need to make sure that you keep the ground loop as small as possible. And even if you're using a differential probe, if the common mode rejection ratio is not very good, you'll still see some of the common mode noise coming through. With this amplifier, you get very high common mode rejection, so really clean measurements even in very noisy probing environments. So there's a second solution, which is a newer solution from LeCroy to solve this measurement problem. So the DA1855 is still a great solution for this, but we've come out with a series of scopes now, which we call our high definition oscilloscopes. And what the high definition scope is it's got a really low noise, pristine signal path front end, and then it has real 12-bit digitizers, 12-bit ADCs inside of the scope. So this gives us a much lower noise measurement with a much higher dynamic range. And you can see the difference, the 8 bits capture on the right here, looking at that saturation voltage, versus the 12-bit capture on the left. So, for example, in a single quantization step that we see in the 8-bit scope, there's actually 16 different steps in the 12-bit scope. So that's what gives you this much cleaner picture here of the signal. But you still have an issue even with the HDO scopes, because you have to use some probe to get the signal into the scope. And now if you stick a noisy probe with a low accuracy in front of the very high performance scope, you've sort of ruined a lot of the performance benefit that you're getting from the HDO scope. So we've come out with a few probes now that are matched to the HDO to give you similar accuracy and noise performance that you're going to get on the HDO. So this way you have a full measurement system that's going to have that high performance that you're looking for in this measurement. So here's comparing the 12-bit scope, or HDO scope, with our standard probe, and then here's the 12-bit scope with our 1% accuracy probe. And you can see the difference here. So this is going to have a better DC gain and low frequency accuracy spec. And you can see the difference. We have a cleaner signal over here with a nicer shape. You can also see the DC voltage here. This is 0 volts, so it's very nicely aligned in terms of the DC offset. There may be some adjusting you want to do with that anyways, but this is really going to give you a nice measurement here. So this is a second solution. You have the DA1855, and then you have the high definition scopes here. And what's nice about the HDO approach is that you can capture the whole signal at once, and you can make all the measurements in one shot. You don't need to zoom in to make the conduction loss measurement and then zoom out to make other measurements. So you can get the whole thing in one high dynamic range capture. So these are some of the probes we've come out with to match that capability of the HDO scopes. So this is the HVD 3102 and 3106. They're different bandwidths, high voltage differential probes. And on the left we have our new CP030A and 31A current probes, and these are going to give you, again, a higher accuracy, a higher sensitivity measurement with the current probe here. Of course, you have the option of using the DA1855A along with the HDO scopes, and that's really going to give you the best result for this measurement. So here's an example of looking at that. And now, if you're using this kind of approach, what you want to do is actually measure the RDS on, or the dynamic on resistance for this state, and we have an automated measurement that'll do that. And then you can plug that back in to the switching measurement, and that'll calculate all the switching measurements, loss measurements at once using the value that you measured from this zoomed in view here. So it's a few other sources of error to kind of address. You know, that the one we just talked about is really the difficult one to address. We have a few others here that are pretty easy to fix. So in order to get the best loss measurements, you need to adjust the DC offset and the skew for both the current and voltage probes. And the way to adjust the DC offset is, here's one approach we can use, is to take the power waveform we have down on the bottom, use a math function to integrate the power waveform, and that's going to give you this energy plot up here. And if we look at that, what the state we want to really look at here is the off state. So in the off state, we know that we shouldn't have any power loss because we shouldn't be conducting any current during the off state here. So what we want to do is adjust define adjust DC offset until we see this energy is very flat during that state, or you can look at the off state measurement here and adjust it until we see this is minimized. Now the other piece we need to adjust in order to make very accurate turn on and turn off loss measurements is the skew. So these are going to have, you know, some pretty fast turn on and turn off times, and so if there's any skew in between the voltage and current probes, that's going to really introduce a big error into our measurements. So at Teledyne LeCroy, we sell a fixture here which puts out a synchronized voltage and current pulse, and you hook up your probes there, and then you can deskew the probes so that you make sure you have no skew between those voltage and current signals. And that'll allow you to make a very accurate turn on or turn off loss measurement. So here's an example. On the right-hand side here, I'm showing the power waveform and the loss measurement on the bottom here. This is before performing the deskew. And you can see we're measuring about 13 microjoules, and you can see kind of this big spike here. And then after performing the deskew on the left side, we're only measuring about 7.8 microjoules, and you can see how much the power waveform has gone down here. So just kind of a small bump. And I just overlaid the two up here, so before and after the deskew, so you can see it's really just a very small change here that has almost a factor of 2 difference in our loss measurement here. So another measurement that you might be interested in making on the transistor itself is to look at the safe operating area. So typically in a data sheet for MOSFET, for example, it's going to tell you what the maximum voltage and the maximum current and the maximum power are for that device. And so what you can do here is we can plot an XY display of the voltage versus the current. So what we have here is, you can see on the x-axis is voltage, the y-axis is current. So you have voltage here, current here, and it's going to take both of the input waveforms here, the voltage waveform and current waveform, and plot them on a single display. And the benefit here is we can look at, make sure that it doesn't exceed the max voltage parameter, doesn't exceed the max current, and it doesn't exceed the max power, because we have all the information plotted in one screen here. And you can change these variables down here to design a mask that fits for whatever the spec that you have for your device is. And you can see if you have some violation, it's going to mark that with these red circles so you can see anywhere that it's violating the mask. Okay, the next piece here is the transformer. So any power supply system where you need to have isolation between the output and the input, which this is true for any AC to DC supply, less so for some DC to DC supplies, but some of them do have transformers as well. So the transformer gives you the isolation here, but this is also another source that you can have loss and other effects inside of the transformer here. So we have some measurements in the scope that allow you to characterize the transformer, the actual magnetic material inside of the inductors there. And typically, the measurements that people are looking to make here is to look at the magnetic flux density, the magnetic field strength, and then plot those two together, again in an XY display here, and this gives you the hysteresis loop for that magnetic material that you have in the core. Okay, so how do we actually get these B and H plots? So once we have the B and H plots here, it's pretty easy. We can plot them in an XY display and you get the hysteresis loop, but how do we actually get these is an interesting question. So the first one here we'll look at is the magnetic field strength, and so that's just the magnetic field that's generated from the real current in the coil. And so here we have our voltage signal and we have our current signal, so we can take our current and multiply it by the number of turns in the number of windings, and divide by the magnetic path length, and that'll give us the magnetic field here. So these are some variables you need to plug in yourself. We're going to take the current waveform that's measured and we're going to do the calculation and give you the result here. So that one's pretty easy to get. But the magnetic flux density here, B, this is really generated by the magnetization of the material itself. And so that's a little bit more complicated to get to because, well, we don't know much about the magnetization. But we do have this voltage signal up here. But one thing we can do is look at, this is Faraday's law here. And initially this doesn't look that helpful, but I was listening to a talk by a pretty smart guy, and he told me that there was no such thing as voltage, which really blew my mind since I work for a company that makes equipment that measures voltage. But his point was that if you look in Maxwell's equations, there's no mention of voltage, but what you have is this integral of the electric field along some path. And really, when we talk about voltage, this is actually what we're talking about. So this is really just voltage on this side. And on the other side, well, we have this piece here, this integral, and this is just the B, which is what we're after, but dot dA, and since the magnetic field is going to be normal to the cross-sectional area, then this is essentially what we're looking for, this piece, this B here. So all we have is we just need to integrate the voltage with respect to time, and that'll give us B. And sure enough, if you take the voltage waveform and you do an integral math function, this is what you'll get. So now we have our B waveform and our H waveform, and we can plot our hysteresis loop. And we're going to make these slides available. I think they're already available. You can click the section on the panel there and download it. So this is just kind of a reminder of some of the stuff I said here if you want to refer back to it to know what the H and B and how they're calculated. But once we have that, we can plot this hysteresis. And this is interesting here because basically as you magnetize the material, once you reduce the magnetic field down to 0 again, there's still some residual magnetization of it, and so there's some work then to do to demagnetize it before you can flip it the other direction. And so this is going to give you that information. Also, if you take the ratio of the magnetic H and B, that's going to give you the permeability of the material. And the permeability is going to actually change as you change the magnetic field, so it's not a constant. And you can here you can see we've used some parameters here to look at the B and H and divide them here to give us the permeability. And so you can use cursors to sweep through these and measure all these things. Okay, so that was the transformer here, and now I want to kind of keep moving to the output, towards the output here. And ultimately this power supply is going to have to supply power to some load. And so I've inserted something into the diagram here, which is a switch and a load. And then we want to look at how the feedback mechanism here, which we take a look at the voltage here, we feed it back into this controller through some isolation. And then the PWM controller actually says, okay, I need to provide more power or less power depending on the voltage we measure there. And then it's going to decide how it wants to control the gate here in order to accomplish that. So it's interesting to have this switch up here because now we can look at how the controller behaves under dynamic conditions under a step load condition. So here we're looking at, again, the same kind of thing we were before. So we have our voltage up here, our current down here, and you can see it goes through all the states of the switching cycle. But now I'm probing another piece here. This is in channel 3 is the gate drive signal. So this is the signal that's being fed from the PWM controller to the gate, and this is actually going to, when it goes high, is going to close the transistor, and we can see them are low voltage and conducting current. And the way that it's going to supply more power to the load is to use a wider pulse here. And if you need less power, it's going to use a narrower pulse. So this is an interesting signal to be able to look at here because now we can look at this over longer periods of time and understand the behavior of the control loop itself. So the way we're going to do that is with something called a track function. So the parameter track is a math function that LeCroy invented many years ago. And what we do is we take a waveform like you have up here, and this waveform is going to be voltage versus time. And we're going to measure some parameter. So in this case, we're going to measure period. We're going to measure the period of every cycle in the waveform here. And then we're going to take each of those measurements and we're going to plot them down here. So in this axis, we have period is the y-axis and time is the x-axis. So what happens is we measure the first cycle here, has some period that's plotted here. The second cycle is slightly larger, so you can see the waveform goes up. Third cycle is narrower, so we go down, and so on. And we create a waveform that is that parameter over time. So this is really useful for a lot of applications, but looking at a pulse width modulated signal, and this control loop is one of them. So here's an example where we have some load. So this is the load current here. So we have some current flowing, and then all of a sudden we disconnect the load. So we open that switch, and now there's no current being drawn from the power supply. And if we look at up here, you can see that you have these nice wide pulses, and as soon as we disconnect the load, the pulses get narrower and narrower. And as that happens, you can see the track function is going to decrease. Now eventually it's going to stabilize out to some new pulse width here, and we can look at the time that it takes from the load change condition till when we achieve some stability here. And we can look at this settling time, which is interesting. So this allows you to plot the dynamic behavior of this control loop and how it responds to different conditions. Here's another example where now we're connecting a load, so you can see the current jumps up quite a bit here, and like you'd expect, the pulse widths are going to respond by getting wider and wider, and it sort of overshoots the mark and then takes some time. You can see we haven't even, in this case, acquired enough data to really capture the final state here. So for these types of measurements, it's really useful to have long memory on your oscilloscope, so that way you can maintain a high enough sample rate to capture those narrow pulses, but capture enough time so that you can see the behavior over a longer period of time. So for example, here we're showing a startup, so just turning on the power supply and seeing the behavior as it powers up. So you can see there's all kinds of weird stuff that happens right at the beginning here. Then it kind of ramps up and finally settles out to some constant pulse width here. Okay, the final section I'm going to talk about today is the DC output here. And this can really be for either a AC to DC supply or a DC to DC supply. So in either case, you really want to understand how, the whole point of this product is to take some input power and deliver some nice clean output power at a certain voltage or a certain frequency or whatever it is you're looking for in the output, but you want it to be well controlled. So we want to definitely look at the DC output to understand if we're achieving the kind of power that we want to. So one of the main things for a DC output we want to look at is the ripple. So as a part of the power analyzer package here, you can see we can set up a ripple measurement, and it's showing here the ripple voltage, and then we're actually showing a zoom in here, so you're able to see, for example, you have these big spikes when the power supply is switching. And we can also view the harmonic content of it down here by looking at the spectrum. And the spectrum display is also displayed up here in this by labeling the peaks here. So you can see, if you have a switching frequency, you'll typically be able to see that as the biggest peak here, and then various harmonics. We can also view the ripple in our standard spectrum analyzer display here. So this is a spectrum analyzer option that we have on some of our scopes. It comes standard, some it's an extra software option. But this allows you to take your time domain voltage output signal here. This is nominally a DC bus, but has some ripple on it. And then we can use the power analyzer again to display the peaks here. And it's going to allow you to also display a table with the frequencies and amplitudes. So if we look up here, in this case, this is a 2.9 megahertz switching regulator. And sure enough, we can see a frequency right here, 2.956 megahertz. And then various harmonics and other AC components that are on this power rail. So what's really nice about the spectrum analyzer feature here is that instead of an FFT where it's sort of difficult to figure out how to set up what you actually want to see, with the spectrum analyzer you're able to set the start and stop frequency like I've done here, or you can choose the center and span frequency. You can choose resolution bandwidth, or there's an auto mode here as well. You can implement different kinds of averaging or max hold. And then you can also show a spectrogram and some other options, and then the automatic peak detection and labeling. So it gives you an interface that's a lot like a spectrum analyzer on your oscilloscope. So this particular switching regulator is actually powering a clock, a 10 megahertz clock. And so the next thing I want to do is look at how that ripple that we saw on the power rail is going to affect the performance of this clock. And so if I look in this case, this is using our Jitter kit software. And our Jitter kit software allows you to analyze clocks and other types of signals to look for jitter on them. And it gives you a lot of different views. So you can see kind of a persistence display here, a histogram over here, or a track. But I really want to draw your attention to the jitter spectrum. So this is displaying a frequency domain view of the jitter on that clock that's being powered by that regulator we just looked at. And I zoomed in here to show you a peak, and a peak is going to be any kind of periodic jitter on the clock. And sure enough, you see a peak here right at 2.956 megahertz. And if you remember from the last slide, that was the exact frequency of the ripple on our power rail. So this is due to the switching regulator, the output there. We can see that jitter coming through onto the clock. So there's some things you can do to solve this kind of problem, or maybe you don't need a clock that's that stable and this is not an issue, but either way, you have a lot of nice tools here that allow you to at least understand what's going on and address some of the issues and verify the performance of the power system and the downstream components as well. Okay, that wraps up the webinar today. I wanted to leave some time for any questions that we had. So thanks everyone for your attention, and I'll open it up to questions.
Okay, thanks, Stephen. So as Stephen said, if you have any questions, please go ahead and send them. You can use either the chat section of your control panel or the actual questions section. Okay, so we did have a question earlier. Hold on one quick second. A couple of people have asked if this was being recorded. It has been recorded and will be available later today as an on-demand webinar. Another question: when measuring noise of power using switching regulator, I see the inductor noises being picked up, but the ground section of the ground section of the probe. This inductor crosstalk noise would not be picked up if I use a more distant ground. How can I prevent this phenomenon?
Okay, so I talked about this a little bit, but I'll explain a little bit more in detail. If you're using a single-ended probe to make any kind of measurement near a power supply, and actually this is true for any single-ended measurement, you have an issue, which is that you have some ground lead on the probe. And the typical configuration most people will use the probe in is there's this long alligator type lead that comes with the probe, and it's maybe 5 inches long and has the alligator clip on the end. And so if you're using that kind of lead, what you've done, if you connect that on to the ground on your board, you've created a big loop, and that's going to act as an antenna picking up any noise, switching noise, and anything else that's nearby. So in a really noisy environment like a power supply, that's going to be a big issue. So if you're using a single-ended probe, the key is to actually use a ground as close as possible to the signal you're probing and use as short of a ground lead as possible. So you can, a lot of the probes will come with kind of a spring attachment for a ground, or a little kind of knife blade attachment. Short, low inductance ground leads, that's the way to go. Of course, better than the single-ended probe is just to use a differential probe. So differential probe you can use in a single-ended mode by connecting one of the sides to ground. And in that way, if you have any interference that's picked up by the probes, typically it's going to be on both probes, and when it goes into the noise goes into the diff amp, it's going to all get subtracted out. So the diff probe is definitely the way to avoid that issue, and that's where that high common mode rejection ratio comes in. So the DA1855 is really going to solve that problem for you, or the HVD probe that we're selling as well. That's going to solve the problem. If you have to use the single-ended probe, make sure you use as small of a ground loop as possible.
Okay, thanks, Stephen. All right, we just got a ton of questions, so bear with me. How would you make measurements of current when the current exceeds 1,000 amps? How do you make high bandwidth measurements in that case?
So well, high bandwidth is relative, but for the probes that we sell at LeCroy, we only sell up to a 500 amp probe is the max. Beyond that, you're typically using, there's a couple companies. You have Pearson makes a current transformer, and you have Rogowski coils and other things that are sort of for higher current applications. And those you can integrate with the scope using our rescale function on the scope. So you just connect it up, and the transformer needs to have a voltage output, otherwise you put a sense resistor in there. So using one of these other current transformers, you get a voltage signal into the scope. The transformer is going to have some spec, which would be, it's like 10 amps per volt or something like that. So you can put in that scaling factor into the scope, and it'll read out in correctly scaled amps.
Okay, Derek, hopefully that helps. If not, you can let us know. The next question is, Edward, what technique did you use to measure input and output simultaneously? did you float the scope?
So to measure input and output simultaneously, you need 4 probes for single-phase applications. For a 3-phase application, we sell an 8-channel scope that allow you to make an efficiency measurement even with 3 phases. So that's something that we have some other webinars that are going on right now. That's called the HDO 8000. But for the single-phase case, you only need 4 probes, so it's fairly easy to make. We don't need to float the scope because we can use a differential probe. And that's really the key. Anytime anybody asks me about floating the scope, the answer is always differential probe. So differential probe will give you the isolation that you're looking for. Otherwise, you need to worry about tying the ground from the scope to basically non-ground on the device, and then you can short out the device. The other problem is if you're trying to capture multiple signals, the grounds between the channels are not isolated. So the differential probe gives you the isolation. Again, you're just going to ground one of the sides of the differential probe, and then you have a fully isolated input. So I never recommend floating the scope. That's can be damaging to the scope. It's also a dangerous thing to do.
Okay, so Edward, hopefully that helped. If not, let us know. Next question is from Grant. What probes do you recommend for 800 volts DC bus systems that use 1200 volt silicon carbide FETs that can have ringing to over 1000 volts?
I think the HVD 3106. So that's our new series of probes. That's again has the really high accuracy. That's meant to go with the HDO scopes. So those will do up to 2000 volts peak. It's 1000 volts RMS, and so that should handle that application. We're also working on coming out with some even higher voltage probes along the same kind of line, but that'll handle that application that you're talking about. And those HVD probes are also good for the 120 volt, 240 volt, or 480 volt kind of applications as well.
Thank you, Stephen. All right, the next question is from Ben. He asked if we have any tools to measure the losses in the output inductor.
So you can also, the tools I described for the transformer, those are also valid for the inductor. So to measure the magnetic properties of that material, which is really going to tell you about the loss through there, so the same BH curve and all that kind of stuff is going to be useful for the inductor measurements as well. There are some other factors that also contribute to the loss through the inductor or the transformer, like the size of it and things like that. I'm not an expert on power supply design or those kinds of things, but the same tools that we use for the transformer measurements, the BH curves, those are going to be useful for inductor measurements as well.
Thanks, Ben. I just sent you a note in case, make sure that answered your question. Next one is Oleg. He asked losses. Okay, for measurement of power switch losses, what is a limitation for settling time? You mentioned 100 nanoseconds settling time. This is too long for 500 kilohertz. How fast a switching can you handle?
Okay, yeah. So if let me look back back here. Whoops, sorry. So if you look at, for example, one of these pictures here. So again, that DA1855, the differential amplifier, that's going to allow you to do this right here and overdrive the signal, but it's going to take some time even for that amplifier to recover from saturation, and the spec was less than 100 nanoseconds. So in this case, you're looking at 500 nanoseconds per division, so it's sort of one of these smaller divisions here. So if you have a really fast switching device, that may be too long. Okay, you can't wait 100 nanoseconds because it's already switched the other direction. So 100 nanoseconds is basically 10 megahertz. So if you have a power supply switching frequency in the megahertz kind of range, this DA1855A is not going to work for you. And really what you should be looking at is the HDO scope along with the HVD probes. So in this case, we're not overdriving the amplifier at all, so we don't need to worry about that recovery time. We're able to capture the whole signal, and we're able to have high enough dynamic range to be able to handle seeing the full signal and not overdriving, and zoom in and see the details of the saturation voltage here. And the HVD probes are going up to 120 megahertz, so that should be plenty of bandwidth for, well, you're sort of maybe borderline there, but it should hopefully be enough bandwidth for what you're looking at, depending on how fast the switch is. There's some new kinds of switches that are coming out now that are adding, more of a challenge, but those are not widely adopted yet, like the gallium nitride and stuff like that. The wide band gap materials, they switch a lot faster, so it's very hard to measure those on scopes these days, because you often have this bandwidth limitation. But
okay, hopefully that helped. I just sent you a note if not. Next up is Hussein. He wants to know how can I find out about output caps quality?
So I think we can just look here, for example. Yeah, so the output has some caps and some other stuff that's going to filter the signal to ultimately give you this DC output. In terms of looking at the quality of the caps, I'm not sure if you mean just the quality of the output voltage, but I mean just looking at the ripple on the output voltage is going to tell you if you need to add different caps or inductors or things to try to filter that more. So I'd really be looking at the ripple measurement to try to tell me about what sort of output filtering I should add.
All right. One more question. Question is from Zenu. You mentioned that a differential probe is not accurate when it's saturated, but what if I don't saturate it? Is the measurement reliable?
Yeah, definitely. So in this case, we're overdriving the probe like crazy. This signal here is going through the roof of the building, and that's what's causing the inaccuracy when the probe comes back into its region here. Now, if you do a measurement like this, so here we're using a differential probe. We're not saturating the amplifier. We're not overdriving the signal off of the scope display, and we're going to get a nice accurate measurement here. Now, we're going to get a more accurate measurement with this probe, but it's the same concept here. We're not overdriving the signal, so we don't need to worry about the overdrive recovery spec. We can just zoom in and look and see the signal here. And this is where, again, the HDO 12-bit scope comes into play, because we can zoom in and we can see the signal with sufficient resolution without overdriving the signal off the screen. If you only have an 8-bit scope, when you zoom in, you can't see the signal with sufficient resolution. But yeah, if you don't overdrive it, you don't need to worry about that. You're going to get a nice accurate measurement here.
Okay, so I think that's it. Hopefully that answered everybody's questions. We appreciate you joining us today. Stephen, I don't know if you have any final comments?
Oh, thanks for attending, and yeah, send an email or if you have any other questions, and we can get back to you.
Yeah.
Okay, thank you.
Great. Thank you, everyone. Have a good day.